Dear students, in our previous lecture, we learnt about non-homogeneous differential equation of order 2. Now here we are going to learn higher order non-homogeneous differential equation. In particular, we are going to solve a problem on non-homogeneous equation of order 3. So the method of solving a non-homogeneous equation of order 3 is given here. That is, the equation L of y is equal to y triple dash plus a1 y double dash plus a2 y dash plus a3 y equal to b of x. Now because the right hand side we have b of x, it is a non-homogeneous equation. The most general solution of this equation is given by xi equal to the particular solution xi p plus phi, where phi is given by C1 phi 1 plus C2 phi 2 plus C3 phi 3. We have three solutions here because it is an equation of order 3, where this phi 1, phi 2, phi 3 are linearly independent solutions of the homogeneous equation L of y equal to 0. That is, we have to consider this equation to be equal to 0, and then we have to find these three solutions phi 1, phi 2 and phi 3 and substitute here and obtain the solution phi. Next, to find the solution xi p, it is given by u1 phi 1, u2 phi 2, u3 phi 3, where the functions u1, u2, u3 can be obtained by the following, where we have the derivatives of these functions u1 dash, u2 dash and u3 dash. That is, u1 dash is equals to Wronskian 1 of x b of x divided by Wronskian phi 1, phi 2, phi 3 of x. Similarly, u2 dash we will have this change alone. Here Wronskian 1, here Wronskian 2. And u3 dash is given by w3. So Wronskian 3. Remaining the denominator and b of x, all this is same for these three. Where this Wronskian, the denominator, the Wronskian of phi 1, phi 2, phi 3, three linearly independent solutions is given by, we know that the Wronskian is obtained by the determinant. Now this Wronskian of phi 1, phi 2, phi 3 is equal to the determinant of phi 1, phi 2, phi 3, phi 1 dash, phi 2 dash, phi 3 dash and phi 1 double dash, phi 2 double dash, phi 3 double dash. This is how we find the Wronskian. And what is this W1, W2, W3? It is actually, if you see here, W1, W2, W3. In general, I will write it as WK, where K will be equal to 1, 2, 3. It is the determinant obtained from this Wronskian, the Wronskian of phi 1, phi 2, phi 3. So first we have to find this determinant, and in this determinant, if we are finding W1, then this first column has to be replaced by 0, 0, 1. If we are finding W2, first and third column will remain the same. The second column alone we have to change as 0, 0, 1 column. That is very important. If we are finding W3, the third column has to be changed as 0, 0, 1 and these columns will remain the same. This is how we find W1, W2 and W3, and after finding we have to substitute here. And to make it simple, to find the Wronskian, we will be using the formula for Wronskian which we have learnt as a theorem previously. The formula for Wronskian is given by e power negative a1 multiplied by x minus x naught Wronskian of phi 1, phi 2, phi 3 of x naught. In particular, we take the value of x naught to be equal to 0 and substitute here and generally find the Wronskian, where this a1 is the coefficient of y double dash. If you see here, the coefficient of y double dash is a1. So this value we have to consider and we have to substitute there to make it simple to find the Wronskian. Maybe if we do a problem on this, you will understand it better. So now let's see a problem on this topic. So here we have an example. The question says that find the solution xi of the equation y triple dash plus y double dash plus y dash plus y equal to 1, which satisfies these given conditions. So let us see these conditions later. Now first, the given equation is this. So this equation has to be taken and written here as L of y equal to y triple dash plus y double dash plus y1 plus y equal to 1. we see that this is a non-homogeneous equation of order 3, because the right hand side is not equal to 0, it is equal to 1. So this is a non-homogeneous equation, and the higher derivative of this equation is 3. Therefore this is a higher order non-homogeneous equation, and the degree of this equation is 3. That is the order of this equation is 3. Now from this we have to compare with this equation L of y equal to this. So from this b of x is equal to 1, and a1 we will be in need of this a1 while evaluating Wronskian. Previously I have told you. So this a1, so from while comparing with it, we see that the value of a1, which is the coefficient of y double dash, is equal to 1. So a1 is equal to 1, and the value of b, so b of x is 1, so therefore b of x is equal to 1. So first we have to obtain these two values. After that we have to find the solution. We know that the most general solution xi is given by xi p plus phi. Now we have to evaluate this phi, where we know that phi is equal to c1 phi 1 plus c2 phi 2 plus c3 phi 3, where phi 1, phi 2, phi 3 are the linearly independent solutions of the homogeneous equation L of y is equal to 0. That is, this L of y, this polynomial, we have to equate it to 0. So we know that the characteristic polynomial will be r cube, and then plus, here we have a y double dash, so r square plus, for y dash it is r, for y it is a constant 1, because so 1 equal to 0. Now this polynomial has to be resolved. We have to factorize it to find the roots. Let us use the method of synthetic division in order to solve this. So if we see, while using the method of synthetic division, first we have taken the coefficients of r cube, then r square, r, and then the constant term 1. So let us check whether negative 1 is a root or not. Okay, we have to check with 1 and rule out the case, and then we can check with negative 1. So if we do so, here we will have 1, and here negative 1, 0, 0, so 1, negative 1, and we see that it has a remainder 0, which means that one of the value of r is equal to negative 1. So we have evaluated one of the value r. Now the remaining polynomial, here using this is the coefficient of r square, r, and the constant term. So r square, r is 0, and the constant term is plus 1 equal to 0. So r squared plus 1 is equal to 0, from which we obtain r squared to be equal to negative 1. So we obtain that r is equal to plus or minus square root of negative 1. So therefore the value of r is equal to plus or minus square root of negative 1 is I. So this is an imaginary root. So the three values of r is r equal to minus 1, and r equal to I, and r equal to negative I. So we have to now write the solutions. So now because we have three roots here, the first solution phi 1 of x, and all the three roots are distinct. Phi 1 of x will be equal to e power r1 x, and then phi 2 of x we have to write. Okay. So now we have to write phi 2 of x, but we observe that the roots are imaginary. So now we can take it like this. So phi 1 of x, we will take it as the root will be actually e power alpha x, and then cos beta x. And then phi 2 of x, so this I will just strike it off because the roots are imaginary. I am doing it in this way. Phi 2 of x will be e power alpha x sin beta x, and then phi 3 of x will be equal to e power, that is here we have the third root, e power r3 x. So now we shall substitute one by one. If we see here, r is equals to plus or minus I. So from this we see that the value of alpha is equal to 0, and the value of beta is equal to 1. That is, it is the imaginary part. So beta is equal to 1. The real part alpha is 0, and the imaginary part is beta equal to 1. So in that case, now this phi 1 will be equal to, that is phi 1 of x will be equal to e power alpha x. So e power 0x cos beta x, so cos x. And then phi 2 of x, the next one, phi 2 of x will be equal to so here we have e power 0x sine beta x, so sine x, and then we have phi 3 of x, the third one, which is equal to e power r3x. The value of r3 is equal to -1. So the next root is -1. So it is e power minus x. So this is what we have. So more simply, this will be actually phi 1 of x will be equal to e power 0 is 1. So it will be equal to only cos x. And then phi 2 of x, e power 0 is 1. So that will be equal to sin x. And then phi 3 of x is equal to e power negative x. So now the general solution phi we will write, which is equal to c1 phi 1 of x. So c1 cos x plus c2 phi 2 of x. So c2 sin x plus c3 e power negative x. So we have found the solution phi. Next we have to find the particular solution xi. We know that the particular solution xi is given by, here we have, the particular solution xi p, which is equal to u1 phi 1 plus u2 phi 2 u3 phi 3, where u1 dash, u2 dash, u3 dash is given by this. Now for this, to evaluate this, first we need the Wronskian of x. So first we will evaluate the Wronskian of x. The formula for Wronskian of x is given by this. So using this, we have to evaluate the Wronskian. So let us see that now. So now we have to evaluate the Wronskian of phi 1, phi 2, phi 3, which is equal to the determinant of, first is phi 1 of x, which is cos x, and then sin x, and then e power negative x. Now next we have here phi 1 dash, that is differentiation of this, which is negative sin x, and then phi 2 dash, differentiation of this is cos x, and differentiation of this is negative e power negative x. Next phi 1 double dash, so the differentiation of this one, which is negative, for sin x it is cos x, for cos x it is minus sin x, and the differentiation of this will become e power negative x. So this is the Wronskian. So this one we have to find the determinant of this. So this can be simply done by using the Wronskian formula, that is the formula for Wronskian. That is, we know that, so we will generally write it as w of x for convenience, but it means that w of phi 1, phi 2, phi 3 of x. Okay, so e power negative, in the beginning we saw a1. So what was a1 equal to? It is equal to 1. So that one we have to substitute. So a1 is 1, and I have already told you, let's take the value of x naught to be equal to 0. So what we will do, we will take x naught to be equal to 0. In that case, it will become x minus 0, and then Wronskian of phi 1, phi 2, phi 3 of x naught, but x naught we have taken to be 0. So we have to evaluate Wronskian of 0. So at this place we have to substitute 0. So we have to check out this determinant when x takes the value 0. So let us see that now. So when x takes the value 0, that is phi 1, phi 2, phi 3 of 0 is equal to, so whenever x is 0, this determinant becomes cos 0 is 1, sin 0 is 0, e power 0 is 1. So it's like that. And then here we have sin 0, so 0, cos 0 is 1, e power 0 is 1, but we have a negative sign there, so negative 1. And here cos 0 is 1, so negative 1, sin 0 is 0, e power 0 is 1. So the value of this determinant gives us the Wronskian of 0. So we can just expand this using the, taking the first column, we can find the determinant. So 1 multiplied with 1 times is 1 minus 0. And then for this, anyway this is 0, so that term will go away. So 1 multiplied with, we should block this and this, so 0 into 0 is 0, minus into minus will become plus, 1 times is 1. And so this value will be equal to 1 multiplied with 1 is 1, plus again 1 multiplied with 1 is 1, so this value is equal to 0. So the Wronskian of 0 is equal to 2. So now this 2 we have to substitute here. So to find the general Wronskian. So therefore the Wronskian of x will be equal to e power, now x minus 0 is x only. So e power minus x, and then this multiplied with 2. So this is the value of the Wronskian w. So now this has to be used in the formula. That is wherever we have the Wronskian, we have it in the denominator, right? So here we have to use that. That is, we have to substitute 2 e power negative x. Now to find u1 dash we need w1. To find u2 dash we need w2. To find u3 dash we need w3. Now to find w1, w2, w3 in this Wronskian, that is the Wronskian that we have here in this determinant value, to find w1, these two columns will remain the same. This column alone we have to change it as 0, 0, 1. If we want to find w2, these two columns will remain the same, and this column alone we have to change it as 0, 0, 1. And if we want to find w3, these two will remain the same, and this will change as 0, 0, 1. This one I have told you while giving an introduction of about this problem. So if you would have listened it carefully, you can understand it now. So this is what. So let us do that now. So now u1 dash is equals to this formula where this w1 of x is equal to, in the Wronskian, that is in this determinant, we will change this as 0, 0, 1. So it will be 0, 0, 1, the first column alone. The remaining will remain the same. So it will be sin x cos x minus sin x, and then this will be e power minus x, negative e power negative x, and then e power negative x. So this is the determinant that we have to find. We can expand this determinant from this first column. So it is plus minus plus. So 1 multiplied with, so this and this we have to block. So w1 of x will be equal to, so blocking this and this, sin x into this. So minus e power negative x sin x. So multiply this, minus e power negative x cos x. And so we obtain w1 of x to be equal to, we can take this negative sign outside, e power negative x outside, and here we have sin x plus cos x. So now we have obtained w1 of x. Now we have to substitute this w1 of x in this formula to obtain u1 dash. So let us do that now. So if we see here, u1 dash will be equal to, so here we have to substitute w1, which is negative e power negative x multiplied by sin x plus cos x multiplied by b of x. So in the beginning I have told you b of x is equal to 1. So b of x is equal to 1. So that one we have to substitute here. So multiplied with 1 divided by the Wronskian. What is the Wronskian that we have obtained? W of x, which is 2 e power negative x. So it will be 2 e power negative x. So this and this will get cancelled, and therefore our u1 dash will be equal to minus 1 by 2 sin x plus cos x. Now this is u1 dash. From this we can obtain u1 by integrating this u1 dash. So let us see that now. So integrating this with respect to x, so u1 dash dx will be equal to negative 1 by 2 integral sin x dx. We are integrating it separately. Integral cos x dx. So therefore integration of u1 dash is u1, which is equal to negative 1 by 2 multiplied with integral of sin x is negative cos x, and then integration of cos x is plus sin x. So this is what we obtain. So this is our u1. In a similar manner we have to obtain u2 and u3, which I will show you, but you just try the workings, okay? So now here we have evaluated u2 dash, which is equal to Wronskian 2 of x b of x by Wronskian of x, where w2 of x is given by, if you see that it is the Wronskian determinant of the, that is, it is the Wronskian where the second column alone is 0, 0, 1. Remaining is all same. So when we expand this determinant with this, with respect to this one, it is plus minus plus, plus minus, and then I'm sorry, this is minus. So minus plus minus, so it is minus 1, blocking this row and this column, cos x into this. So we have this negative sign, cos x into e power negative x. Minus into minus becomes plus, sin x into e power negative x. So e power negative x is common, so multiplying this negative sign inside, it becomes cos x minus sin x. And then we have to substitute in u2 dash. So u2 dash is this. So if we substitute w2 here, and b of x is 1, and then this is w, this and this will get cancelled, and u2 dash is 1 by 2 cos x minus sin x. So u2, by integrating this, integration of cos x is sin x and integration of sin x is minus cos x. So minus into minus will become plus, so plus cos x. This is u2. In a similar way, we have obtained u3 dash, here, that is u3 dash is given by this formula. So where w3 is the Wronskian with the third column alone taken as 0, 0, 1. So when we expand with respect to this sign symbol is positive, so 1 multiplied with this into this, which is cos squared x, minus into minus plus sin x into sin x, sin squared x. So cos squared x plus sin squared x is equal to 1. From this, when we substitute in u3 dash, that is w3 is 1, b is 1, this is the Wronskian w. So this, when taken to the numerator, it becomes e power negative x becomes e power x divided by 2. So when we integrate u3 dash, we get u3 which is equal to the integration of e power x is e power x only divided by 2. Now this we have found u1, u2, u3. Now we shall substitute in our particular solution xi p. So now here I have taken and written phi 1, phi 2, phi 3, u1, u2, u3. And we know that xi p is given by this. So when we substitute this over here, xi p will be equal to, now what is u1? Minus 1 by 2 multiplied with minus cos x plus sin x multiplied with phi 1. Phi 1 is cos x. And then plus u2. So what is u2? This. So plus 1 by 2. Okay, 1 by 2 sin x plus cos x multiplied with phi 2. Phi 2 is here sin x. So multiplied with sin x plus u3. u3 is e power x by 2. So e power x divided by 2 multiplied with phi 3, which is e power minus x. So e power minus x. So if we see 1 by 2 is common throughout, so we can take that out. So when we take it, we obtain this to be equal to, so 1 by 2, and this negative sign, when I take it inside it, this becomes positive. Cos x into cos x is cos squared x, and then this becomes negative sin x cos x. So sin x cos x. Then after this, that here sin x into sin x, so plus sin squared x, and then cos x into sin x is, so plus sin x cos x, and then e power x, e power negative x is 1 because these two gets cancelled and it becomes 1, so plus 1. Now if we see these two terms gets cancelled, cos squared x plus sin squared x is 1 and 1 plus 1 is 2. So that will be equal to 1 by 2 multiplied by 2, which is equal to 1. Therefore xi p is equal to 1. The particular solution xi p is equal to 1. So now we can write the most general solution xi. The most general solution xi of x is equal to xi p plus phi. So when we substitute that, it will be equal to xi p is 1 plus phi we have already evaluated, which is this. So phi is equal to c1 cos x plus c2 sin x plus c3 e power minus x. So we have to substitute this. So let us do that here. So after substituting, we obtain this. So 1 plus c1 cos x plus c2 sin x plus c3 e power minus x. So this is the most general solution xi of x. Now to evaluate this c1, c2 and c3, in the question they have given some initial conditions. That is, they have given xi of 0 is 0, xi dash of 0 is 1, xi double dash of 0 equal to 0. So using these conditions, we can evaluate the constants c1, c2 and c3. So let us see that now. So first condition given is xi of 0 is equal to 0. So if we see substitute this, we obtain, so xi of 0. So when we put 0 here, this will be 1 plus cos 0 is 1. So c1, sin 0 is 0, and then e power 0 is 1. So plus c3 is equal to 0. From this we obtain an equation c1 plus c3 is equal to negative 1. So let us just have this equation. The second condition given is xi dash of 0 is equal to 1. Now if we see here, xi dash of x is what actually? So xi dash of x will be equal to 1 becomes 0, and then in differentiation of cos x is minus sin x. So minus c1 sin x, and the differentiation of sin x is cos x. So plus c2 cos x, and the differentiation of e power minus x is minus e power minus x. Now it is given that xi dash of 0 is equals to 1. So if we put 0 here, sin 0 becomes 0, cos 0 is 1. So this implies that c2 minus e power 0 is 1, c3 is equal to, it is given to be equal to 1. So this is another equation that we obtain. The third initial condition given is, xi triple dash of 0 is equal to 0. That is, we have to differentiate this again. So xi triple dash of x is equal to what? When we differentiate sin x, it becomes cos x. So minus c1 cos x plus minus c2 sin x, and then plus c3 e power negative x. Now if we put 0 here, from this we obtain cos 0 is 1. So minus c1 sin 0 is 0, e power 0 is 1. So plus c3 is equal to 0. So this is the third equation that we have. So we have obtained these three equations. So first we will solve equation 1 and 3. So if you see, equation 1 is c1 plus c3 equal to minus 1. Equation 3 is minus c1 plus c3 is equal to 0. So when we solve this, these two gets cancelled. So 2c3 is equal to minus 1. So from this we obtain c3 to be equal to minus 1 by 2. So this is the value of c3. Now substituting the C3 as minus 1 by 2 in this equation 1. So we will get C1 minus 1 by 2 is equal to minus 1. So from this, C1 will be equal to minus 1 plus 1 by 2, and that is C1 is equal to minus 1 by 2. So the value of C1 is minus 1 by 2. Similarly, C3 is equal to minus 1 by 2 can be substituted here. So from that we will get C2 minus into minus will become plus 1 by 2 is equal to 1, and from this we obtain C2 to be equal to 1 minus 1 by 2, and the value of C2 to be equal to 1 by 2. So therefore the value of C1, C2, C3 are obtained here. So after obtaining the values of C1, C2, C3, we have to substitute it in this most general solution, that is xi of x equal to, in this we have to substitute C1, C2, C3. So after substitution what we obtain is, so we obtain xi of x to be equal to this. So simplifying this furthermore, this will be equal to 1. We can take the negative sign outside, 1 by 2 also outside. So here we get cos x minus sin x plus e power negative x. So this is the most general solution of the given third order differential equation. So this is a very significant problem in the examination point of view. Hope you have understood it. Thank you.